All right, now that we've got this great formula that describes the electric field total in a thin ring as it goes around, let's see if we can clean this up a little bit. Looks like we can move some things around. Let's look for some constants. And then when we integrate, let's just bring everything outside the integration sign. So we've got the electric field total. All right, let's look at the constants here. We got 4, yep. Pi, yep. EO, check. Lambda, the density, yep, that's never going to change. I mean, density of a substance, object, is going to be the same no matter what. ds, trouble, variable. Constant, z, that's the distance from the center of the ring out to point P. Never going to change. R, the radius of the ring itself, no change there. So we've got a collection of constants that we can move outside. So we've got 1 over 4 pi EO. Lambda z divided by z squared plus big R squared to the 3/2. All right, so far we've got that outside the integration sign, and then we got integral ds. All right, so integral ds obviously is fairly easy to solve. All right, and we can do that. Now, the question is, what are we going to use for boundaries? So as we go around the loop, we can start at 0 on one side of the loop and use that for the beginning spot. As I walk my way around the loop, all right, how far are we going to go? Well, it's a circumference, it's a circle, all right, and we're going to end up going around 2 pi big R all the way around. So our boundaries are going to go from 0 where we start all the way around one circumference of the ring, which is 2 pi big R. All right, so let's see if we can insert a couple things. One other thing to note. If we're going to be given a problem, they're probably going to tell us the total charge of the ring itself. They're not going to tell us what dq is. They're not going to tell us probably what the charge density is. They're probably just going to tell us the charge of the ring. So why don't we replace the density with big Q divided by 2 pi r? Well, remember, Q is the total charge. They're going to give us that and the radius of the ring. So let's make that substitution in our next little round here. So I've got 1 over 4 pi EO, and instead of writing lambda, I'm going to write Q divided by 2 pi big R. All right, that leaves us a z up in the top, divided by z squared plus r squared to the 3/2. All right, now when we integrate ds, integral ds is obviously just plain old s. And once again, our boundaries go from 0 to 2 pi r. All right, so let's make some substitutions here, and let's plug in a few things here. All right, so we end up here. I'm going to leave the 2 pi r just the way it is. I'm inclined to do some combinations here, but I think I'm just going to sit on that for just a little bit. All right, so let's plug in some more stuff here. So we've got 1 over 4 pi EO, Q up in the top. All right, we've got our z divided by z squared plus r squared to the 3/2. All right, now when we make our evaluation, when we put in our values, are we going to replace s with 2 pi r? So as we do that, we're going to end up with a 2 pi r up in the top like so. And then when we do our subtraction for the other boundary, minus, well, we place the s with a 0. Isn't that going to negate this entire thing? So we're going to end up with minus nothing. All right, so we end up with just this. Let me get rid of the 0 because we don't really need that. Well, some good things are starting to happen. I forgot to put the 2 pi r underneath the q. Sorry about that. So what's going to